Thank you, Bill, Max, for the introduction, also because of the nice talk from Tonya. So I'm going to introduce you today on some applications of the floating experiment that Bill showed, as well as some evaluations that I have been doing both in Italy and also the warm or fresh out of the oven seismic hazard models in New Zealand and Europe. So also talk about some of the lessons that we have been having in the evaluations of the last experiments and results, and also more importantly, some prospects of what we can do onwards. So basically, this is already has been spoken, but I think one of the biggest benefits that we could have, that we had from the CSEP experiments, was the definition a priori of the state in which the models will be competing in a fair way, where the evaluation metrics were defined, where the authoritative data sources were defined, and all of the models had a common set of rules upon which they were evaluated. So what hasn't been spoken is that some limitations had arisen at multiple stages of CSEP, of the past experiments, which were related basically with some theoretical aspects of the likelihood or the likelihood-based hypothesis done on the underlying Poisson assumption, especially in time-dependent forecasts. This is kind of a personal opinion. We can disagree on that, but one of the things that happened is that the hypotheses were implicit within each model. For instance, a model which built on faults, so we can say, okay, faults can be useful, but that's not necessarily proving that faults are actually useful. So the hypotheses were not explicit in the experiment. So basically, the only scientific question that we had in many experiments was which models performed the best. And that's actually not necessarily a scientific question, but rather practical towards operational earthquake forecasting or seismic hazard assessments. One of the other things that we already spoke is about having a monolithic software design. And then it was quite hard to reproduce, not reproduce, but rather reuse the code that was developed in the previous experiments. So I'm going to continue a little bit of the definition of floating experiments that we have been working on. So basically, this has already been spoken, is that we try to develop experiments that satisfy the standards of new open science and scientific coding. And for that, we make advantage of modern tools of data storage in open science repositories like Zenodo, code versioning, Git mainly, and also software and dependencies packages, which was an additional topic in which we're using tools like Docker to try to contain all of the set of instructions that are going to build the computational environment of both my time-independent or time-dependent models and so on. This is basically. Sorry, Bill, I copied it. So yeah, I think this can be spoken here. So we try that floating experiments basically can be easily deployable by a user that does not have a huge expertise in programming. We will attempt that is thoroughly documented both how it is to define experiments and also all of the set of instructions that can be found there. And of course, these experiments should be open to the community, and hopefully all of the official experiments can be periodically with results that are published periodically. One of the things that I wanted to mention is that for sake of simplicity, and I think it's part of a nice thing, and all of this scheme is that while we kind of download or clone all of the code from GitLab or Zenodo that defines the experiment and the models, we can create, or let's say, a containerized environment in which we build experiments in our local machine. We can run it, can get the results. But in case of unofficial experiments, it's not that anybody can open and publish the results of an experiment. That should be at least agreed with the institutions that are running the experiment, or all the developers that are working on it. So these are clearly examples that are quite known, like creating experiments for the scientific purpose, validating operational earthquake forecasting models, and also analyzing the components of seismic hazard models. I think one of the interesting extra uses of this concept of experiments is that actually, as a user that creates a model, we can pretty much design our own experiment using the same system and create our own prospective experiment, which is actually a really good scientific practice. So basically all of the models that one creates to represent natural phenomena, their validity or their use comes how they explain unseen data. So what a better way than a prospective experiment. So in the following slides, I'm going to present you some examples of the application of these experiments. A little bit of shifted. There are work that has been done a little bit before, but everything will be shown in the context of these open experiments. So first, I'm going to show you how to evaluate previous experiments. So we have all of the source codes for the experiment of Italy that was kicked off in the 2010. We have two forecast examples that are shown also with the graphic of PyCSEP. Pretty much all of the figures are done with it. One of the left is the smooth seismicity model adapted from someone that's around here. I don't know if you know. And also the right is the this seismic source model of the old Italian national hazard model, which is being updated now in 2020, 2021. It has a lot of bumps to go through. So we can do all of consistency tests that actually are like a sort of intramodel hypothesis to see if the data, observed data, is actually consistent if the model was the true data generator. So we can see that some models work, some doesn't, but that's not what I wanted to show actually. So the important thing to know, or what I wanted to share, is that I think all of the evaluation metrics that we have provided, they just show us an aspect of the forecast. Just let's say like log likelihood scores, they show us, for instance, they're really strong on penalizing false negative, basically if an earthquake occurs, where it didn't have assigned probability. So that's just one aspect of the forecast. So it's important that we kind of go with these new experiments in a multi-metrics approach. So we have different metrics that use different aspects of the forecast. So I think this was done because of a lot of criticism that this experiment had, that everything become like a horse race. But rather, it's important to see also the uses of these experiments. So what we have here is a couple of metrics, different metrics. We have the log likelihood score, the Breyer score that was suggested in the last year by Francesco Serafini, and some other scores, and also the Poisson consistent. So what we do is basically order in the wheel. Where we have our most performing models at the clockwise there. And one of the main observations that we can see is basically that the old 2004 source model of the Italian seismic hazard model, it's pretty much on the top performing. So it's under these optics, under these metrics, it's kind of say, okay, we haven't progressed that much in terms of which model is the best fitting. However, if we kind of group all of the forecasts in terms of their ingredients, we can start seeing some patterns in a qualitative fashion. So basically here we have categorized by model ingredients, let's say. So first, we can see is that most of the models that include some sort of fault information, whether it's what are using faults to delineate sites seismicity properties within, they are actually in the best performing site. Another thing that is interesting is that we have three different catalogs: a historical catalog, a catalog that goes back to a century, and a catalog that goes only 2 decades. So most of the best performing models are actually showing that the long historical catalog and the century catalog are actually performing well. Whereas the models that use only short-term catalog, high quality instrumental catalogs, are actually quite at the bottom. One other interesting thing is that actually the models that include the spatial variability of the p-value actually are kind of in the bottom. So what I wanted to show you with this is not necessarily which is the best performing model. I wanted to start thinking that how can we actually test all of these models ingredients quantitatively, not only qualitatively. And there are many interesting experiences with these p-value spatial variant models. For instance, in the Emilia sequence, these especially p-value varying models, they have like a really high probability of it occurring in certain cells. And immediately the next cell, they had a really low probability. They were really spatially precise. And because of that, they completely failed. But we're not able to tell whether the hypothesis of a spatially and temporal varying b value is actually useful or not. And that happens because we cannot analyze that because we don't have the source codes of the models that were employed in the beginning. So that, I think that's where we should move forward to test rather a scientific hypothesis and not only a horse race of the best performing model. So what I'm going to show you here is kind of an example that we have been developing with Bill and many others from the INGV, that we want to design a new forecasting experiment that kind of tackles all of the difficulties that we have been having in the past experiment. So we're going to go full-time dependent, creating forecasts of one day, basically. We're going to tackle definitely catalog-based evaluations, no question here. And one of perhaps, this is all what I've shown a little bit about the open floating experiment. I think the only difference that I want to highlight is that this part that we have here is that a model is creating their own models with their own programming language, with their own syntaxes, and a lot of things that are difficult to homogenize. So what we're trying to create is a model interface from the experiments that can be harmonized across models, but without losing the model particularities, basically. So for that, we're using Docker that's defining all of the environments, whether it's R, Python, all of the library dependencies, etc. And we're trying to make it speak with experimentation. So for that, we're working with Modelless from ETH and INGV that are trying to create a certain standard of how models could be published to be experiment ready to participate in experiment. So in the current time, we're working with 7 modelers of the RISE project, but we plan to open this experiment or an open call in January. Had really good news. I have been showing a little bit of the experiments in Europe, and it's been incredible to see how many modelers are actually interested in participating, people that participate in the conference, but they're not only modelers, they're actually providing new test metrics, like coming with this blurred distinction between modelers and testers, and that's really nice, and they're really motivated to provide metrics to be standardized in SPICE-CSEP and also their models. Yeah. Can I ask you the time? All right. Excellent. And another thing that I want to push forward, maybe it's going to be difficult, but I really want to go into a model hypothesis testing. Like, a really important question is regularity. Like, how much my model predictions will change if I use a 20-year catalog, or if I use a 25-year catalog as an input. So how much the final solution is dependent on the initial conditions, basically. I want to study the parameter space or hyperparameter space of some models. I know that most of them are self-calibrated and with 0 degrees of freedom, but there is every model has assumptions and parameters really. So we need to test those. And also would like to go for model subclasses, whether they use sort of the clustering algorithm, whether they use something that's not necessarily quantifiable, like the parameter space, but still is important to put into analysis. So that's with the time dependent. It's an experiment. I'm going to show you some, let's say, use cases from the open experiments that we have been running, and particularly with the European seismic hazard models. So this is the 2013, the older model where we have certain components of the source model in terms of seismogenic source forecasting. And we have a component that's really dark here, like the classic area source, uniform rate areas. We have another model that is based on explicit fault lineaments with slip rates and maximum magnitudes that are constrained with the polygons. And we have a completely smooth seismicity forecast that combines faults and seismicity. So here on the right is the smooth seismicity model. Um, here we have the same area source model. Looks kind of spatially varying, but we need to put this there. So we do a prospective test in the sense that we are using unused catalog from 20, not even the catalog that was, I'm going to explain something. So the catalog used for this model was until 2006, but the model was released in 2014. So yeah, one could say we should do prospective experiments between the unused data between 2007 and 2014, but that's actually being suited prospective. So the important thing is to do a testing when this model was released. So we make sure that every models do not have a bias or about certain model, because for instance, this model actually, the catalog did not contain, for instance, Blackula. But kind of a modeler, we have to say, okay, maybe we need to explain Blackula. And so on. So what we can see is basically in a conditional likelihood, the air resources and the smooth seismicity model work quite fine, but as the people in Europe know, or like the people that work in the seismic hazard model, the models that include faults and polygons embedded in these polygons actually work quite bad. And it didn't have to do with the definition of faults. It actually had to do on how they were too rigid on defining fault geometries, that when the earthquake happened really next to it, it was inside a polygon, but the polygon did not have the magnitudes, like high magnitudes that the fault had. So that made them fail completely. Although, let's be honest, an earthquake happening really close to a fault can be considered. So there's a problem about over definition probably that needs to be worked on. And that's what they did. So the new seismic hazard model now, instead of having necessarily these polygons, they continue using the classic area source model, but now they are using the faults and combining it with smooth seismicity. The logic tree became a little bit more complex. So they're using different magnitude distributions, different slip rates, different maximum magnitude or corner magnitudes. So some example of tests, we have all of the models, all looks good except this one. So that's actually a kind of, they try to use an alternative distribution, the Pareto one, and that's actually the one that's failing. So not to say that the Pareto distribution works bad, but the interesting question is actually why. I don't know. I don't have the answer yet. If we test all of the components from this new hazard model, we can see that basically all of the faults and smooth seismicity are working quite neatly. This is in comparison with the old smooth seismicity model, and all of the error sources are kind of indistinguishable. So they must have been doing something right. Time. Okay. All the same concept applies to the New Zealand experiment. We have a raw, really complex logic tree. This logic tree that has different components is going to be trimmed basically on which will have the greatest impact or that have a significant impact on the end mean hazard. But we can still start designing this experiment. The model will be releasing 1 to 2 months, so we can start testing the source component. For now, I'm limiting to the crustal source models. We have different flavors of hybrid or merging data sets forecasts. We have different components like additional flavors, like do we put EPAS into every earthquake is a precursor according to scale from David Rose methods. We also are applying a certain floor to the low seismicity areas because we got to acknowledge that probably we're putting too much spatial resolution into low seismicity. So, okay, let's check out the results in the last 2 years. So, indistinguishables, except this one that's a little bit red there. It's kind of not working quite right. And all of the S-tests, especially, they're really consistent. So, okay, we're doing good until we see actually that we only have 3 earthquakes to test all this. So we actually don't have substantial results yet in New Zealand. But that means that it's really important that we start with this experiment now, or at least block the model so we can go forward in the next years until we have significant data. I think he's already Bill spoke, but I just wanted to show you that this is a work we've been doing with Asim actually has been doing in GFZ. So he's creating a spatially varying resolution and test what are the limits of spatial precision that actually increase performance. I think the thing that I wanted to show you about that is actually open uploaded experiment. It's been you have all of the source code, and we're publishing certain tags or branches that are blocking the experiment and showing the results so far. So it's got all of the code is there, and it has a neat report where you can see actually the test results or observe what's written there and what hypotheses are we testing. So to finish, I think I just wanted to tell you, speaking about, okay, should we test our models? There are a lot of people that has criticism on testing our models. I just wanted to say that, okay, this is a really known phrase by Pauli, actually. So he said that, okay, an unfalsified model is not only not right, it's not only wrong. So what can tell us that? I think it's important to define how new emerging data will support or refuse a model hypothesis. That's for me the key. In Spanish, we say I have a glass roof on top of me while I'm saying this because I still have to figure it out my models, how to test my hypothesis, and so on. I think there is also, I don't know if you agree, it's kind of polemic synthesis, if we can discuss that. There is a new effort, actually, in submitting our gold standards, techniques, and knowledge to the test. Let's say how this algorithm of smooth seismicity, the same one, applies or can work everywhere. How vanilla e-test is performing everywhere. And when you develop a model, it would be better that you always test your models versus these less or no hypotheses or less informative in the information theory sense. One last point, I think we should have stopped the concept that a model being rejected or performing poorly, it has a negative connotation. My point of view is that the negative performing models or the least are the ones we can draw most interesting discussions, actually. If a model is performing better, okay, so what? Okay, we use it in the next seismic hazard model or so on, but maybe it doesn't tell us anything new. This is a common sentence that I would say that all models are wrong, some are useful, elegance will suffice. I mean, some people say, okay, give me 3 parameters and I can fit an elephant with it. But yeah, this is right, but this only should be valid on the support, on the light of new evidence. And I wanted to finish with that sentence. So